Okay, so let's discuss a question from riveted joints. Basically, we are given with a double riveted double strap butt joint. So in the cross section, let's say you have these two plates which are connected by butt joint, so there will not be any connection directly between these two plates, and you have one strap here as well as a strap here. Okay, and so on each plate you'll have two rows. That's why double riveted. So it's always per plate, per your main plate, how many rows of rivets are there. So there are two rivets here. My drawing may be out of the mark, but then okay, this is so two rows, so double riveted. Okay, and two straps, one at the top. This is your strap 1 and this is your strap 2. Okay, so now when we are asked to calculate strength of riveted joint, we always consider three things, three cases: tension, shear, and crushing. Okay, now tension is for the plates, okay, for the main plates, okay, and which basically we call as tearing of the plates. Okay, so let's start with that. So tearing of the plate, you have to understand that if you look at the picture for the main plate, okay, what happens at the main plate is that you have two rows. Let's remove the rivets here and put the hole size. So hole size will be your, assuming that the clearance given is, the rivet size is 7 mm. Okay, the rivet size is 7 mm, and the dia and the clearance, assuming that it's a diametric clearance, so this 0.5 and this 0.5, so the hole size, the rivet hole size on the plate will be 8 mm. Okay, so that is your clearance. Okay, and per pitch, if you are asked to find out, okay, per pitch, so this is my pitch, and so this area is the lowest area, and in this cross section per pitch only this area will be able to resist. So we are calculating only per pitch length how much load comes, if it is failing in tension or tearing, or if it is failing in shear, or if it is failing in crush, and then we take the minimum of that becomes the strength. So per pitch length, this is the minimum area, and we take this minimum area. So this area will be pitch length into the diameter of, minus the diameter of the hole, half here and half here. So pitch minus diameter of the hole, okay, into the thickness of the plate. So this is the area that is resisting, and so assuming that this is on the verge of failing, so it will be supporting the shear strength in tearing. So sigma T into P minus TH into, now this doesn't depend on, because this is at every cross section and we are taking at the minimum cross section of one row, so this can be taken at any row. So number of rivets or the rows of rivets doesn't matter here. So this is my load in the tearing which it can support. So sigma T is given as 120, okay, into pitch is given as 28. If you look at this problem, 120 is the tension, that is the tearing strength of the plate, and 28 is the pitch, minus the diameter is 8, okay, and the thickness is 5. So this value comes about 12,000 newtons, which is 12 kilonewtons. So we'll keep this in mind, 12 kilonewtons. Now coming to the shearing, now this will be interesting. Coming to the shearing, per pitch length, if this is the top view, so per pitch length, okay, it tries to shear here, 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 and here. So I mean, how much, what is the contributing area? The contributing area, this is one rivet on the top. If you see this cross section, when I try to apply a force here on this plate, this half of this area, so that makes one rivet, and it makes one rivet here. And you have a, so there is two contributing areas, two rivets cross section at here, and also two rivet cross section here, because it's a double strap. I mean, so you have contributing area 2 at this cross section and at this cross section 2, and that will support the entire load P. So P is basically 4 into 4 pi by 4 d square, so that is the total contributing area, into the shear strength is the load in the shear which it can resist. So it's 4 into pi by 4 d square is the diameter of the rivet, which is 7 whole square, and shear strength is 100. So this value comes about 153.8 Newton, and that is 15.3 kilonewton. So this is 15.3. We're going to come into the crushing. Now crushing is when you apply a load like this, how much area. Now let me draw this picture again here. So when I apply a load P, there will be a diameter here. Okay, so this part of the rivet will be in contact here. Okay, and here also. I mean, these are the parts. So the entire load will be basically withstand by this part of the rivet. Okay, and there you have the localized compressive stress, and that localized compressive stress should not go beyond the actual compressive strength. The localized stress, compressive stress, shouldn't go beyond the compressive strength, otherwise it will crush. So how much is the contributing area per pitch? So this is 1/4 of the rivet, this is 1/4 of the rivet. Okay, so this makes, I mean, like this area is what we take, the superimposed area is what we take. So this is this area, which, so let's say you have one rivet here, so this area, it will be exerting a pressure like this, so the load supported by each of the rivet will be sigma into dt. That is for one rivet, but you have half the rivet here and half the rivet, that makes one rivet, and here also, so it's 2 sigma dt. Okay, that is what is the crushing load. I mean, you try to understand this. Let me explain. So one rivet, if it is a full rivet, the stress is sigma, so sigma into this is diameter into the thickness, and it will be acting throughout this. Okay, the resultant load on the left side, whenever you have a semicircular distribution kind of a stress, the resultant load will be on the left. The resultant load is something like hydraulic pressure acting on semicircle, so it will be sigma into d into t, the superimposed area, d into the thickness of the plate. This is coming from the one rivet, but if you take per pitch, so these two form one rivet, one rivet area, because half is gone and half is gone, so half plus half is 1, and you have a 2 rows, so the entire 2 rows will be supporting the crushing load, so it is into 2. We try to understand this is very important. So sigma is 150, diameter 7, thickness 5 into 2, so this comes about 10500 newtons, that is 10.5 kilonewtons. So out of this, the strength per pitch is minimum of these. Now why minimum? Because all these are failure mode, so you have calculated the worst load in all the cases. Okay, the tearing, the shear, and crushing. So minimum of that is what is the maximum you can apply, because then you can prevent 3 of them, right? So minimum is 10.5 where it will fail in crushing, so this is the maximum you can apply, and that is your strength joint. So 10.5. Let's look at the option. The option is B. This is a very good question. The max you can go in a machine design in riveted joints. Thanks.